Looking at this 3D wireframe mesh as it transitions into a human femur, we have to approach the human body from a strictly engineering perspective. We are examining a complex mechanical, material, and spatial system. This analysis will bypass biology. We are not studying physiology, pathology, or how the body heals from disease. For the biomedical engineer, anatomy is the rigorous study of spatial geometry. It is the precise mapping of physical boundaries, load-bearing structures, and mechanical interfaces. Any mathematical model attempting to simulate joint stress or fluid dynamics will fail entirely if the exact physical boundaries of the surrounding human structures are ignored. In this split screen, the robotic surgical arm on the left is dictated by the exact geometric curves of the human spine on the right. Every advanced biomedical output relies on this biological structural data. To map this system, we have to analyze it across a strict progression of scale, starting from the microscopic material properties and building up to macroscopic mechanical assemblies. A precise anatomical understanding is the prerequisite blueprint required to build any functional interface between external technology and the human body. Before drafting a single mechanical schematic, an engineer must define a universally standardized point of origin. In medical engineering, this absolute spatial origin is known as anatomical position, standing upright, facing forward, with palms open and directed outward. This diagram illustrates how we map biological space by dropping a grid of 3 intersecting geometric planes directly over the origin point. The first division is the coronal plane, separating the front from the back. A sagittal plane then splits the body down the absolute midline, and a transverse plane cuts horizontally across the waist, locking the figure into a 3D grid. With the grid established, directional terminology translates directly into spatial vectors. We map the axes using specific Latin pairs: superior and inferior, medial and lateral, anterior and posterior. The superior-inferior axis dictates the vertical coordinate scale, mapping the y-axis from the top of the head down to the feet. The medial-lateral vectors establish distance from the system's core center line along the x-axis, tracking outward toward the limbs. Finally, the anterior-posterior vectors define depth and surface proximity, tracking through the z-axis from the chest through to the spine. Surgical navigation software and patient-specific CAD models use these exact spatial vectors to orient cutting tools and position implants relative to the surrounding tissue. Medical directional terms act as the strict Cartesian coordinates required for accurate 3-dimensional reconstruction. With the macroscopic coordinate system set, we have to drop down the scale to examine the microscopic raw materials that fill the grid. This flowchart tracks the biological structural hierarchy. It starts at the individual cell, networks outward, and consolidates into a solid 3D block of tissue. Looking closer at the block's architecture, cells are surrounded by an extracellular matrix. This matrix is secreted by the cells themselves and forms the physical scaffolding of the human machine. Despite its complexity, the entire system is constructed from a catalog of only 4 fundamental tissue types. Epithelial tissue serves as the structural boundary layer. It lines cavities, covers surfaces, and acts as the primary environmental interface. Connective tissue operates as the primary load-bearing matrix. It forms the bones, tendons, and structural glue holding the assemblies together. Muscle and nervous tissues complete the system by acting as the kinetic actuators and the high-speed electrical wiring. Because these tissues are highly organized, they exhibit anisotropy, meaning their physical properties change depending on the direction of applied force. A tendon resists tension lengthwise, but compresses easily from the side. This microscopic visualization demonstrates that behavior under load. The fibers within the tissue stretch and align in parallel, demonstrating how histological architecture dictates mechanical resistance. Accurate finite element modeling of human structures is impossible without inputting the foundational material properties dictated by this microscopic tissue architecture. Scaling back up, these discrete tissues weave together to construct organs, which operate mechanically as macroassemblies. In this exploded 3D render of the musculoskeletal system, we can analyze the primary rigid linkage framework of the body. The skeleton is divided into the axial system, the central, static, load-bearing elements, and the appendicular system, the kinetic levers. Alongside these rigid linkages, we can map the cardiovascular routing pathways of the body's closed-loop plumbing. To reverse engineer these assemblies, engineers face a problem of structural visibility. The geometry of a joint looks entirely different depending on the modality used to visualize it. This comparison illustrates the problem. On the left is a standard exterior view of an intact knee joint. On the right is its exact interior cross-sectional density, captured in a sagittal MRI slice. Designing a knee replacement requires tracking a single geometric landmark, like the curve of the femoral condyle, simultaneously across the colorful external illustration and the grayscale internal slice. Radiological imaging, like CT and MRI scans, intentionally strips away color and texture. It strictly captures spatial density and internal material boundaries. By stacking and interpreting these overlapping 2D radiological slices, engineers can build a highly accurate 3D structural model of the internal cavity. This exact multimodal mapping provides the raw data required to train AI segmentation algorithms to distinguish bone from cartilage automatically. Translating accurately between gross exterior anatomy and cross-sectional radiology establishes the absolute ground truth needed for patient-specific CAD design. We have moved from establishing a Cartesian point of origin to mapping microscopic material properties and finally to assembling multimodal macroscopic structures. As shown in this transformation, the synthesis of anatomy and engineering data creates a digital twin, a highly accurate computational mirror. Anatomical study establishes the quantitative framework required for high-fidelity engineering design. This universal, predictable blueprint provides the geometric constraints necessary for all biomechanical modeling. Every advanced prosthetic limb, every surgical robot, and biomechanical interface relies entirely on the precise execution of this blueprint. To engineer any successful physical intervention within the complex systems of the human body, you must first master its architectural ground truth.